Hey everyone, so today we're going to tackle a classic chemistry myth. One of those things you probably learned in school and just accepted as fact. We're going to unravel why some molecules seem to just completely break one of chemistry's most fundamental rules, and how a much better, much more elegant idea has been hiding in plain sight for over 70 years. All right, let's start with a quick trip back to chemistry class. Remember the octet rule? Yeah, that cozy, comfortable idea that atoms are at their happiest, their most stable, when they have 8 electrons in their outer shell. It's the foundation for so much stuff, right? It's how we learn to draw all those Lewis structures. But then you meet these guys, the rule breakers: phosphorus pentafluoride, sulfur hexafluoride, xenon difluoride. Just look at that central atom. Phosphorus is holding on to 5 fluorines. Sulfur is holding on to 6. If you do the math the old way, they seem to have 10 or even 12 valence electrons. So what is going on here? Are these molecules just rebels without a cause? So this whole thing actually has a name. It's called hypervalency. That's the official term for when an atom looks like it's hoarding more than 8 electrons. And for decades, to explain this, chemistry teachers told a story that was, well, it was convenient, but it turns out it was just wrong. Which brings us to that old story. This is the explanation that was passed down in textbooks for years and years, a tale that kind of made sense on the surface, but we now know it isn't really the whole picture at all. The classic story goes something like this. The central atom, let's say sulfur in SF6, just kind of promotes some of its electrons up into its empty, high-energy d orbitals. This supposedly makes more room, so it can form more bonds. And look, it sounds plausible, but it's a clunky explanation. Modern calculations show it's just not energetically favorable. It's kind of like renting a giant, expensive warehouse just to store one extra box, you know? There has to be a better way. And scientists knew this was a puzzle for a long, long time. These molecules were well known way back in the 1930s, but the solution wasn't found yesterday. It was actually proposed way back in 1951 by 2 different chemists, Robert Rundle and George Pimentel, working completely on their own. It just took a very, very long time for the textbooks to catch up. So, it's time to meet the hero of our story. A simpler, more elegant idea that explains everything without needing those clunky, high-energy d orbitals. It's called the 3-center 4-electron bond. Now, the name might sound a little complicated, but the concept itself is just beautiful. A 3-center 4-electron bond is simply a single bond that's shared across 3 atoms all in a line using a grand total of only 4 electrons. That's it. 3 atoms, 4 electrons. No expanded octet needed. So how does it work? Well, imagine 3 atoms in a row, like F, X, E. You take 1 p orbital from each atom and let them overlap. When they do, they create 3 brand new molecular orbitals: a super stable, low-energy bonding orbital, a neutral, non-bonding one just sitting in the middle, and an unstable, high-energy anti-bonding one. Then you just fill them up with your 4 electrons. 2 drop into that stable bonding orbital, and the other 2 go into the non-bonding orbital. And this is the absolute key. This is the whole magic trick. That high-energy, destabilizing anti-bonding orbital, it stays completely empty. The stability of the whole system comes from the fact that all 4 electrons get to sit in the 2 lower energy spots. The molecule is stable, and the central atom never ever had to break the octet rule in the first place. So what does this actually mean for the bonds themselves? Well, you have a total bond order of 1, but it's spread out across 2 links. That means each individual link is effectively a half bond with a bond order of 0.5. And this is brilliant because it perfectly explains why these bonds, when we measure them in the lab, are always found to be a little longer and a little weaker than a typical single bond. The math perfectly matches reality. Okay, so that's the theory. It's elegant, for sure, but does it actually hold up when we look at our rule breaker molecules? Let's put this model to the test. Let's start with an easy one: xenon difluoride. It's a perfectly straight, linear molecule. Well, our model predicts this. The 3 atoms line up, their p orbitals overlap, and they form one simple 3-center 4-electron bond. The xenon atom still has its regular octet of non-bonding electrons, and the whole molecule is stable, simple, clean, no d orbitals in sight. All right, so it works for a straight line. But what about something a bit weirder, like phosphorus pentafluoride? With that complex trigonal bipyramidal shape? How does our simple model handle that? Oh, this is the best part. This is where the model really shines. See, this molecule actually has 2 different types of bonds. You've got 3 fluorine atoms forming a belt around the middle. Those are just normal, strong single bonds. But then you have 1 fluorine on top and 1 on the bottom, forming a straight FPF line. That is our 3-center 4-electron bond. And this perfectly explains a known experimental fact. Those top and bottom bonds are longer and weaker than the ones around the middle. Of course they are. They're half bonds. And we can even scale this up to the ultimate rule breaker, SF6. You'd think it would be super complicated, but it's actually incredibly simple. It's just 3 of these 3C4E bonds, all arranged at right angles to each other, crisscrossing around the central sulfur atom. And just like that, the whole expanded octet problem, it just vanishes. It was never really there to begin with. So here's the most important takeaway. The 3-center 4-electron model isn't just another option. It's a fundamentally better scientific model. And the reason is its incredible predictive power. Let's just recap why it's so powerful. It correctly predicts the linear geometry that we actually see. It naturally explains why some bonds in a molecule are longer and weaker than others. It also explains why you almost always see really electronegative atoms, like fluorine, in these spots. They're needed to pull electron density toward themselves to keep the bonds stable. It even correctly predicts a partial positive charge on the central atom, which matches up perfectly with how these molecules actually react. It just works on every level. And that leaves us with a final thought. For over 70 years, a simple, elegant model has existed that perfectly explains hypervalency. Yet, the old, clunky story of expanded octets is still kicking around in a lot of classrooms. It makes you wonder, right? If a simple model can completely replace a complex rule that we all just took for granted, what other facts in science are just sitting there, waiting for a better, more elegant explanation to come along?